Hi, I'm John Buckley, and my topic for the Industry Research Unit is Falling Weight Deflectometer, or FWD, evaluation of geogrid stabilised test sections in a state highway long-term trial. The research question associated with this topic is how FWD testing can quantify the benefit of geogrid stabilisation in highway pavements. Let's now look at each of these main underlined points individually. To understand geogrid stabilisation, it's important to know the definition of a geogrid. A geogrid is a type of geosynthetic for pavements and reinforced soil. And within geogrids, there are different varieties based predominantly on their manufacturing type. Within biaxial geogrids, there are woven, welded and extruded geogrid types, and you also have multi-axial extruded geogrid types that you see on the right. Pavement geogrids can be classified under either the reinforcement function or the stabilisation function, and both international standard houses, BSI and ISO, that's the British Standards Institution, and International Organisation for Standardisation, have separate definitions for these functions. Improvement mechanisms for pavement geogrids have been very well researched over the years, and here we have 4 of these. The most important mechanisms relevant to permanent pavements are the mechanisms of lateral restraint of the pavement aggregate, the stabilised aggregate, and the stabilisation function. So what are the key features of stabilisation geogrids that relate to these mechanisms? We can see them here. And in summary, the geogrid manufacturing characteristics relate to the stabilisation function, and the rib characteristics of the geogrid relate to the lateral restraint of the aggregate in the stabilised layer. High in-plane stiffness of the geogrid assists both lateral restraint and stabilisation. Numerous studies over the years have examined the stabilisation effect in detail. One of these studies is the small-scale modelling study that was conducted by Itasca in Germany using DEM, or discrete element modelling. You can see the model here. It's a small-scale model because the larger you make the model, the more computing power and time required to run a trafficking simulation. So the model was sized appropriately for a reasonable amount of computing time for each trafficking scenario. There were 2 geogrid types modelled within this DEM setup: a biaxial geogrid, BX2, and a multi-axial geogrid, MX1, and both of these were of extruded manufacture. The advantage of doing this type of modelling is that you can make the layers transparent within the model and see what's going on in various elements within this model as it's being trafficked. On the left, you have the biaxial geogrid, and at the 9th run, towards the end of trafficking, you can see that there's quite high tensile forces, shown in red, within the geogrid directly under the wheel load. And these seem to be anchoring past the loaded area. On the right, there's a different kind of behaviour. You have the multi-axial geogrid response, and you can see that under the wheel load, you have these almost concentric hexagons or near circles forming directly under that wheel load. These are in tension, but the tension's dissipating the further out or the further you move away from the wheel load. And it's also being supported by compression in blue, which surrounds those concentric circles. So there's a much more efficient load spread onto the subgrade with a multi-axial geogrid. You can see that visually. And the tensile loads in this geogrid are about half of those in the biaxial geogrid. A larger scale study was done in 2014 by Penn State University in the US, and it was known as the Smart Rock study. It was a full-scale test setup that comprised 250 mil thick layer of AREMA number 4 ballast, and this is sized between 20 to 50 mil over a large aperture multi-axial geogrid. There was a control section that was run alongside the geogrid section, so this is a comparative study. This research was unique because the authors included a wireless sensing particle called Smart Rock, which was essentially a 3D printed fake ballast aggregate, and this could sense both translational and rotational motion in 3 directions in real time. So both test sections were loaded identically up to 500 cycles of a 13-ton wheel load. Now the results are quite interesting. The video on the left shows how the test setup was loaded eccentrically onto the rail, and this was done to accelerate the testing and get the ballast particles moving as quickly as possible. On the right, we can see real-time movement plots of the Smart Rock particle for both the control section on the left and the multi-axial geogrid section on the right. The red dashed circle that you can see here is the original position of the particle. Now the particle in the control section does try to come back and show some resilience, but it ends up moving further away under this cyclic loading. So it doesn't exhibit a lot of resilience under this type of loading regime. Whereas the geogrid section is really just staying put, and it hasn't moved out of its original position. It may or may not be interlocked with an aperture, but it doesn't really matter, because if it's not interlocked, it's going to be surrounded by particles on every side that are. Okay, so now this completes the section on geogrid stabilisation. The next part of the presentation will involve information on pavement deflection testing techniques. One of the traditional techniques is Benkelman beam testing. It's got a long history of use and it applies the load statically. It is quite slow, so you can't really use it to or afford to use it to test very large networks. It also involves discrete point testing, but it is commonly used. The deflector graph also applies static loads, but it's a continuous test at a speed of up to 4 kilometres an hour. And both of these techniques are truck-mounted systems. So the falling weight deflectometer, or FWD, it performs tests at discrete points and the load can be applied dynamically. The typical test loads are 40 and 60 kilonewtons for standard FWD tests. And it's quite a quick device for testing large networks. The deflections are measured at discrete points from the centre of the load application using geophones. And a typical setup involves 7 different deflection offsets from D0, which is situated directly under the centre of the load, to 200, 300, 450, 600, 900 and 1500 millimetres from the centre of the load. The deflection data from these offsets enables calculation of different parameters which represent performance of different layers of the pavement, as you can see in that schematic there. Sometimes 9 sensors are used for pavements with multiple layers. So this slide shows traditional deflection parameters such as maximum deflection, D0, which indicates overall pavement performance. Subgrade performance is reflected by the D900 offset. Curvature, which is the D0 value minus the D200 value, reflects surfacing, fatigue performance of asphaltic layers. Deflection ratio, it represents cemented materials or base layers, and that's the D250 over the D0 value. Current practice of deflection testing of geogrid stabilised pavements involves Benkelman beam testing used as a post-construction assessment, primarily in New South Wales. It's covered under the R44 earthworks spec by Transport for New South Wales. There are limits on characteristic deflections, which are calculated statistically from the raw data for the top and underside of the selected material zone within the pavement embankment. So stabilisation geogrids have been successfully used to satisfy this criteria for major New South Wales road projects over the years. And there's more information on this in the written thesis. We have some new technology, which is automated plate load testing. It's a state-of-the-art system developed in the US over 10 years ago. So the system applies cyclic loading to pavement layers in a very short time and takes cyclic load and deflection measurements directly. The APLT system measures the influence of the load cycle and the confining pressure on in situ resilient modulus of various pavement layers. It can also be used as a quality control testing regime for pavement construction. So prior research of FWD testing of geogrid stabilised reinforced pavement starts with Gallagher and his co-authors from 2015. 2 trial sections were assessed involving a control section and a welded biaxial geogrid over an existing 150mm thick drainage layer that was stabilised with a multi-axial geogrid composite on a subgrade CBR less than 3. The pavement consisted of, from the top down, 50mm of asphalt, 150mm granular base, 175mm granular subbase, and the biaxial geogrid was installed at the subbase-base interface. A single round of FWD testing was constructed straight after asphalt compaction. The authors only recorded the inner wheel path results. The maximum deflection D0 was higher in the biaxial section than in the control section, which was contrary to expected performance. However, the deflection ratio and the estimated subgrade CBRs from D900 were higher in the biaxial section. Improvements to this research were stated that selection of a greenfield site would have been preferred with more consistent subgrade and moisture conditions to reduce variability of performance. An additional FWD or plate load testing throughout construction was suggested to provide more deflection data on the various pavement layers. Joshi and Zornberg in 2011 reported on a 3-year program of FWD testing that consisted of 9 visits on 32 pavement test sections around Texas in the US. The researchers also did coring, moisture sensing and visual surveys of all of these sections. The sections themselves consisted of controls, 3 geosynthetic sections under the base course, lime stabilised subbase, then combinations of geosynthetic and lime stabilised treatments on a high plasticity expansive clay subgrade. Deflection basin parameters were adopted in lieu of back calculated moduli of the pavement layers. They found that the back calculated moduli really wasn't consistent with field performance. Another outcome from this research was that they identified a minimum conditioning period of 6 months prior to FWD testing, irrespective of the type of test section, whether it was control, geosynthetic or lime. And this was to enable aggregates within the pavement layers to repack and relief of poor water pressures within those pavement layers. The FWD testing showed that the lime treatment improved the subbase deflection basin parameter. However, visually, deterioration was observed over time in these sections, and the authors acknowledged that they needed to do more research in this area. The geosynthetic sections perform well versus both the control and lime treatment sections. The main focus of this presentation is on a trial that was done in northwest Queensland called the Jardine Valley Highway Geogrid Trial. The site was located about 30 kilometres east of Hewenden, and it was on the Flinders Highway, and the total length of the trial construction was about 800 metres. Construction was completed towards the end of September 2008, and there were 8 trial sections in total, and the subgrade conditions were based on a design CBR of 3.5 for a 4-day SATE value. The cross sections of the trial are shown here. There are a couple of thinner sections at each end, but the majority of the sections were 300 millimetres thick and a single layer of TMR type 3.2 material. The geosynthetics used 3 different strengths of extruded biaxial reinforcement grids, BX2, 3 and 4, MX1, an extruded multi-axial stabilisation geogrid, and WG80, a woven reinforcement geotextile with 80 kilonewton a metre tensile strength. Now here is the rainfall history at meteorology stations adjacent to the site. The black arrow here represents the construction of the trial in 2008, and this horizontal red line is the historical average rainfall of the wettest month at these sites, which is January at 112 millimetres. So since construction, there have been quite a few events, and there continue to be high rainfall events near this site. However, I was unable to find any evidence of major inundation at the exact location of the trial. So RoadTech did some FWD testing in January of 2010. There was minimal rainfall leading up to this testing, but there was certainly high rainfall afterwards. The inner and outer wheelpath measurements were done in each westbound and eastbound lane with a 50-metre offset. This is the planned location of the measurement points for this January 2010 testing, and the green stars represent the westbound lane, lane 1, and the blue stars, lane 2, eastbound lane. We can see that we may have a bit of a problem here, and that is that most of the westbound lane measurement points are situated at the junctions of each section. And these are now represented by red stars. So these points were inadvertently sited at these junctions for sections 2 to 8, which really renders the lane 1 data unusable, since you can't assess which section is contributing to the performance, and you have to exclude this data. So in lane 1, there are only 2 points in section 1, here that are green, that could potentially be used. And realistically, the data pool was restricted to lane 2 results only, the blue stars. Because of this, there was definitely a need for a revised and reconfigured FWD testing regime. This was planned and performed by Pavement Management Services on the 26th of November this year. In the 3 weeks leading up to this testing, there was very little rainfall. Learning from the 2010 testing, a minimum 20-metre edge distance was applied from the junctions at the start and end of each section. And to enhance resolution of results in the Section 3 control and Section 5 MX1, there's twice as many measurement points, as you can see here and here. The focus was specifically on the 300 millimetre thick sections, which are sections 2 to 7, and sections 1 to 8 were left out as it was a lot, sections 1 and 8 were left out as it was a lot easier just to compare sections of the same thickness. The full results are in the written thesis, and there's a lot of information there, but I've just summarised that in this table. So as previously discussed, due to the incorrect location of the lane 1 measurement points, there wasn't enough data to statistically analyse the 2010 section, and that's why you see a lot of NDs or not determined in that column there. This table shows the deflection parameters and which pavement layer they correspond to. The actual relevance of these parameters to the type of pavement used in this trial, so that's in this column here. And then the variability of these results for each of the FWD testing regimes, and this is expressed as a coefficient of variation. It was found that there were some deflection parameters that were not particularly suited to the pavement type of this trial, which was a thinly surfaced granular pavement. So there's been research done by Chai and co-authors in 2013 that shows that the D450 and the estimated subgrade CBR derived from this deflection offset is more representative of a thinly surfaced granular pavement than subgrade parameters traditionally derived from D900. So this approach was adopted and was found to have less variability. Deflection ratio values, they proved to be inconclusive for both the 2010 and the 2021 testing. There were quite low CVs, but all of the trial sections were within the acceptable range of good base layer performance, and it was very hard to discern any trend or difference between each section. So that was left out of the assessment. Curvature parameters did have some high variability, And a more representative measure of surfacing performance was discovered, which is the Surface Curvature Index, SCI, or Base Layer Index, BLI, as reported by Hall and Norton in 2019 and Joshi and Zornberg in 2011. This is more appropriate to thinly surfaced granular pavements and is defined as the D0 minus the D300 offsets. A very thorough back calculation process of the data was employed and two back calculation techniques were used. ALIA 1 from the Danish Technical University, there's a reference there for that, Levenberg, and BACFA from the FAA in the US. The main parameter looked at for each trial section during the back calculation process was the variances between the two techniques, and they ended up being quite high, and the back calculation method therefore proved to be inconclusive. So the revised deflection parameters are highlighted in green, and these were used for comparison of the trial sections. These are the summary of the results from the November testing this year for the relevant deflection parameters. You can see that the multi-axial geogrid performs quite well if you compare it to the control. It has outperformed the control in each of these deflection parameters. The multi-axial geogrid section, section 5, is the best performing section with the lowest variability, or CV. Section 7, VX4, had the best performing deflection parameters, but had the highest variability of all sections, so this might warrant further investigation. So in conclusion, and to refresh the research aim, it was how can FWD testing quantify the benefit of multi-axial geogrid stabilisation in flexible highway pavements? The first point to note is that it's very important when setting up the FWD regime to correctly cite the inner and outer wheel path measurement points in relation to where the test sections are physically to ensure you can get useful data. The traditional deflection parameters such as D900 and the estimated subgrade CBR from it and curvature parameters weren't suited to the pavement type constructed in this trial, which was a thinly surfaced granular pavement. More relevant parameters were found, and these were maximum deflection, D0, estimated subgrade CBR from D450, and the SCI or BLI parameters derived from the D0 minus D300 offsets. So in summary, the multi-axial geogrid section outperformed the control section with lower variabilities of these relevant deflection parameters. The current round of FWD testing was quite basic in nature, but a lot more meaningful than the previous 2010 regime, as there was more usable data. So it's suggested to do a follow-up FWD regime in around 2 years, and alongside that, and similar to the research that was done by Joshi and Zornberg in 2011, it's suggested to do pavement coring to confirm pavement makeup, DCPs of the subgrade at certain FWD locations, for example, one in each wheel path for each lane for each section, and then a visual survey of all sections is also suggested. Here are the references that were mentioned in this presentation. There's 3 pages, so I won't go into these in detail, but the full reference list is contained in the written thesis. And finally, I'd like to make some acknowledgements and thanks. And there's a full set of these within the written thesis, but I'd like to mention Professor Frank Bullen as the unit chair for this topic. Many thanks for his patience and understanding and guidance throughout the whole research process. I'd also like to thank my mentor for this topic, John Figueroa. He provided a lot of assistance to this thesis and was very accommodating with his time, experience and knowledge of pavement engineering, and I'm very much appreciative of that. I'd also like to thank the staff at CPEE Admin for accommodating my time frame. So thank you.